political unrest in July, and it's the anti-PowerPoint party. And there is a little small print that says, this isn't just PowerPoint, it applies to any presentation software for the Microsoft friends in the audience. And the elections were held last Sunday, and either fortunately or unfortunately for you, they didn't really do very well in the national polls. I tried to find out the precise number of votes cast, and they keep just getting rolled up into 1% others. So let's move on from religion and politics. And what I'd actually like to talk about is architecture. Back in 2001, so 10 years ago, I was talking at an internal ARM event, and I was kind of laying out what I thought the future of architecture for ARM was. I talked about VLIW, and how that was going to clearly be a significant driver in the future. And let's be honest, I got that wrong. Superscalar, that was a fairly easy call to make, and if you look at the current ARM product lineup, you'll see superscalar products there. And I talked quite a lot about how it was all about building modular systems, and if you look at the complexity of the devices we have today, the investment ARM and the community's made in infrastructure to join IP blocks together, to debug it, to trace it, to test it, there's definitely been significant contributions into making chip design a modular activity. And I also said, the future 64 bits, clearly one day we'll have to do that, and people kind of always went, you never need 64 bits, why are you talking about that, Mike? So I am pleased to announce that today ARM has announced its next generation architecture, which is a full 64-bit architecture. And for those of you who are paying attention, you'll be able to guess in exactly how many slides I'm going to give you any more detail on that. So, moving on from architecture, I wanted to talk about batteries. If you look at it, there's been a kind of 11% historical growth year on year in battery technology. And there's going to have to be continuous innovation to just maintain that 11%. And people are talking about all sorts of exotic anodes built out of carbon nanotubes, and those are the kinds of innovations that are going to be needed to just keep us on the 11%. And I thought I'd compare sort of approximately the same volume, the same weight, a bar of chocolate and a battery from a very popular recently launched phone. And you'll see they're about the same size, about the same weight, significant differences in how much energy is contained in that. So us living in this kind of rather simplistic silicon world, we have our hands tied compared to the kind of guys who are going to do organic computing, because their batteries are a lot better than ours. And if you kind of play that through, it means that devices you have today, even if you just have the same standby currents that the current devices have, you're only really changing a day to 2.5 days. It's not going to make a significant difference. So predicting there around a factor 2 improvement in battery technology between now and 2020. On the other hand, if you look at cellular, there's kind of 3 drivers for where cellular's going: spectrum, technology, and topology. And the spectrum is kind of a scarce resource. It's there. You can't make any more of it. Governments make a good living out of taxing it, as they always will, but there's nothing to be done about it. Then there's the technology side, and there's continued innovation in how do you get more bits down the same amount of RF spectrum. And the last few years have been driven by MIMO technology in base stations. That's slowly starting to play out in handsets. But the main change you can make is in topology. And what topology really comes down to is how dense are your cell stations. And the easiest way to make improvements in the whole cellular infrastructure is to change those topologies and increase the number of base stations there are. And that, if you look at it, is where most of the expected gains come from as you roll from 3G, 4G to 5G. The most significant things will come from topology. There's also been a slight realization that people have been talking a lot about peak bandwidth, and what really matters to the consumer is average bandwidth. And so more attention is being applied onto how you actually deliver high average bandwidth, rather than just claiming you've got the highest peak. And when you put that all together, there's maybe a factor 20 to be had over between now and 2020, or what that average download can be, as long as you live in a well-funded metropolitan area. Right? If you're out in the middle of nowhere, I'm sorry, it's not going to get very much better for you. So, everyone talks about the future and great new things. I think it's time sometimes to stop and think about what of those things that were deprecated and go away. And some of you may remember this. That dreadful pause. Is it going to? And there we are. Well, there's a sound that has gone away from our lives. So not everything is about making things better. Sometimes it's about tidying up and moving on. Back to our friends. No. Cheap. I'm sorry, cheap. E is for eyes. You getting the drift of where this presentation is going? Last year I talked about cubic millimeter systems that we were trying to build to implant in people's eyes to do real-time data logging of glaucoma patients. We finally managed to build a prototype. It doesn't quite meet the cubic millimeter budget. It's just slightly under it. But we're getting there. So we're making progress on those tiny little systems, which I think are an important part of our future. And if you look at display technology and you look at people with reasonable eyesight and two popular phone and tablet form factors, it's clear that 1080p is a good endpoint for the phone form factor, and 4K may just about make it as what you could have on large tablets. Beyond that, any further advances aren't worth it while you've still got your original eyes. But what I think is interesting is if you start looking at power versus content. And if you compare LCDs with newer OLED type technologies, and we're all used to kind of LCDs taking a constant amount of power, but if you look at OLEDs, the power it takes depends on what you're displaying. Black and white pixels take different amounts of power. So it matters whether you're doing web browsing or Photoshop as to what your display is going to use in terms of its dynamic power. And that kind of makes the whole thing more complicated in how you're actually going to drive those systems and optimize them for low power. And of course, video complexity increases as those camera resolutions and displays go up. And you put that all together, and again, I think there's between a 16 and a 64 change in the amount of bandwidth and processing required to just drive conventional displays. F has to be for flash, well, flash and DRAM. And I think, you see speeds doubling every 2 years. The core speeds actually haven't changed that much. It's really the interfaces that have changed. And everyone's been focused on, gigabytes per dollar and peak speeds of gigabytes per second. And again, some of that has forced people to focus into some lower common denominator memory products, which is great from a pricing point of view, but you end up with architectures which don't necessarily give you the lowest power, high performance solutions if you could architect that all from scratch. So I'm worried that in the future, if we continue with the same sort of view on what some of those interfaces look like, you end up with kind of dark bandwidth, which you can't really realize into your processor and SoC. So I think there's opportunities here to collaborate and enable innovation there, and some of that comes out of wide I/O, 3D stacking, and ways of getting realistic bandwidth improvements while still maintaining a realistic power budget. But in general, I see a 32 factor increase of flash and DRAM, and there's always kind of three memory technologies that are about to change the world. And by 2020, one of them may have replaced flash, but we'll see. But whatever happens, I think we'll have a 32 times increase. So now I talk about G, which has to be being a European GSM, and this was my favourite watch. I love the fact that it was a phone, that the user interface was really clean and simple, so I went out and bought one. I have to confess it wasn't the easiest device to actually use. But that's been replaced, and currently my favourite phone is this one, the iWatch, which if you go down on the floor, you'll see they've got it, and it's real, it's here, and it's an Android watch. I like the whole split UI. It uses Bluetooth to talk to your smartphone. It offloads compute onto that, uses that for all of the baseband connectivity. And I think it kind of shows the innovation in devices that are coming. And that'll be launched as a consumer product early next year. So if you take that phone and put it together, I've said there's an order factor 20 improvement in what the radio I/O, whether it's from baseband, Bluetooth or Wi-Fi into those devices. There's going to be 32 times as much memory. There's going to be, 16 to 64 times as much output. Your kids connecting your phone onto big 4K displays, the native resolution and cameras which will have an arbitrary number of pixels because that's a really easy marketing number to increase every year whether or not you actually need it. The bad news, of course, is if you remember we go back to batteries, you have to do all of that with only 2.2 times as much battery because the form factor is fixed, nothing else is going to change. And so the question is, how do you build systems that meet those requirements? And what I haven't yet talked about is, what's the CPU actually doing in there in terms of applications? Right? These are just all the enabling functions that go around it. And for me, the way we're going to have to build complex systems like that in an energy-constrained way is by building heterogeneous systems. And, if you look at the classic compute engines on the right, we've got a big Cortex engine with a large Mali graphics doing wonderful UI and web processing. Last week we announced kind of the big little concept where when you're not doing heavy graphics and CPU intent tasks, which on a phone is a lot of the time, you might just be composing an SMS, you might just be scrolling a simple web page, then you don't need to use the big core, you can use the little core. And as I'll show later, you can make the little cores significantly more power efficient than the big ones. So, big little for different tasks. Some things are perhaps best done with hardware. So you'll see systems with hardware components in them. You'll see systems that then have entire subsystems with their own CPU, their own memory, doing something like audio decode and audio manipulation, because if you want your MP3 player to last for a long time, you want to power down the rest of the system. So again, completely different subsystems. And then there might be, some baseband that does offload, and as those bandwidths to the web go up, there's a big change in what can you actually push off and do into the cloud. And the challenge, of course, is how do you bring those things all together? Whether it's render script, direct compute, OpenCL, they all provide mechanisms that make it easier to kind of plug and play different components so you've got the right compute engine for the right task. It's absolutely not a world where one big solution will solve all of your problems. You've got to do that partitioning. The catch is, there's no automatic solution to the which computing where. It still requires system designers to architect it and say what should run where, when. And I think we're a long way away from being able to automate the generation of all of those different heterogeneous components and make the software seamlessly schedule across them. So there's still, the good news there is, there is employment for good system architects and hardware engineers to do that partitioning. We got a bit of a problem. I did a Google analytic search on Web 2.0, and if you look at the web's Google search trends, you can see that Web 2.0 is going to die on October the 1st, 2021. It's a pretty good linear line. So there clearly has to be something that's going to replace Web 2.0. It's not the Internet of Things, because that search term's kind of gone away. I don't know what it is, but we need something to replace it. But I do passionately believe in the Internet of Things. And for me, it's how it encompasses just about every segment of life that we're in, whether it's from heavy machinery through to consumer products. And with each of those, a whole range of, where do you do it, how do you do it, who do you do it with? And there is this incredible diversity of things which currently tend to live in isolated islands that don't talk to each other. And we'll talk later this morning about some of the things being done to address sustainability, climate change, energy consumption. To achieve those kinds of things, you actually need to have intelligent systems that begin to join together the tiny little cubic millimeter sensors embedded in the concrete of this building, so after the earthquake that I'm told will come one day, you can actually look at it and say, well, what was the stress in that girder? Is the building safe? Isn't the building safe? You need to integrate all of those things. So for me, the Internet of Things is that enormous diversity of things which are currently isolated islands, and when they are interconnected, there will be new services and new improvements that actually improve how we live. J had to be for joules, SI unit for energy, and if I was in Cambridge, I'd sort of talk about Newton, Principia Mathematica in the 1600s and how he came to his realisation about gravity while sitting under an apple tree in his parents' garden just outside Cambridge. And I tried to link that into San Jose, and I kind of struggled because our offices are on Rose Orchard, and I thought, okay, Orchard, maybe they had apple trees, but no, they didn't. So I'm afraid I can't link it back to J for San Jose. But I did find out it was founded in 1777, which was a little earlier than I was expecting, so I was impressed by that. But just to make it clear, kind of, we're interested, on one end in the kinds of systems that run off little nano generators like this that you can start building into objects that generate their power just as you flex them. And I'm not sure when or if we really want to go quite as far as this, which is chips the size of building bricks. But it's an impressive feat of engineering. K was for thousands, and I was intrigued to see that, I could do this all with thousands as long as you put a log scale on the left-hand side. And there's, on top in orange, Moore's law running nice and linear with the thousands of transistors turning into millions and billions. It's a good straight line, and the world has been done very well by that. But if you look at single-thread performance and frequency plotted on that same scale, we all know what's happened. It's all rolled off. There are little increments, because remember this is now a log scale, but there's not a lot more there. And if you follow it through and look at the typical power in watts for servers, that too has reached realistic limits, which mean there's nowhere else to go. So if you've got kind of flattening power budgets, you've got rolling off in frequency, the only thing left to do is to design things with more cores. And there's no doubt that that trend to providing more cores is a good trend for the future. And we strongly believe that the right way to do that is by having a lot of very power efficient cores, rather than perhaps a slightly smaller number of very inefficient cores. And as we enter a world where you've already got scalability into tens and hundreds and thousands of cores, you're through that Amdahl's bottleneck because you're talking about systems that have found other ways to address that. This isn't about single-line compute performance. This is about how do you take racks of servers that provide a web service to tens of thousands of customers simultaneously and make that a lower power, more cost-efficient, lower total cost of ownership solution. So it's about addressing problems that already have scalability built into them. It's the wrong thing to look at how do I just make a processor go faster and faster because you're running out of place to go. The physics just isn't going to work. You have to look at the system, re-architect the system, and solve the system problem. It's not a core problem, it's a system problem. So I'm not sure if this next slide is strictly true. I got it from the web, so I'm going to stand behind that as my defense. But it was doing the benchmarking of, the computer scientist's computer, simply for its beauty, from Cray, through to iPad 2, claiming to have the same Limpact performance. And for me, that just kind of captured, where servers have been, where we've got to, and perhaps where servers are going to go in the future. M is for mountains, and I don't know what your company is like, but in ARM, I sit in lots of review meetings, and people keep having these mountains in them, about this project is going to climb the mountain and get to the top and solve the goal. And I'm always forced to remind people that, you know, most mountaineers die on the way down. So getting to the top isn't necessarily your ultimate goal. But what I was intrigued by was this guy who now works for us, we gave him a job, but who took ARM to the summit of Everest in the 16th of May. And some of our customers, some of you in the room may feel that dealing with ARM is sometimes a bit like climbing Everest. But I liked his kind of understated statements about, you know, how he survived an avalanche and a bit of frostbite. But apart from that, it was okay. So hopefully you find dealing with ARM kind of okay. N had to be, for me, and it's a very personal one, 1998, because that was perhaps a turning point. You might say this is N for nostalgia, but it's actually N for Nokia, and that was the first ever ARM-powered GSM phone. Just to compare that to kind of, you know, where ARM-powered phones have come to today, I just think it's a lovely take on how user interfaces have developed from clean and simple to hopefully simple to use but definitely complicated. O had to be for open source, and I think open source has had a significant impact on the semiconductor industry, and not all of that has necessarily been positive. And I think it's changed the way people view who is responsible for what. And within our industry, that's meant that more and more of the software challenge is actually being pushed down to the semiconductor hardware providers, because it's open source, so you can go and resolve that. It's not proprietary systems locked behind closed doors, managed that way. It's there and available. And so, for me, open source has changed the way people think about things, changes the way about who is responsible for what and how you make your money. Quite independent about any of the ideas of collaboration and open source and community that goes with it. It's the changes in the business models that it's brought about that I think is the significant thing for our industry. P had to be for physical IP. If you look at what we do in ARM, we go from early research chips that my guys in my research group tape out on early unstable processes, which then evolve over time through IP silicon validation all the way up into processor proof points. And the research side may take a couple of years and then maybe a year to actually go through real IP product quality development and proof. And what I'd like to just do is to touch on one chip which was taped out at the end of last year, which was a 20 nanometer test chip that my group do. So if we look at that chip, it was taped out in December, 20 nanometer, about 6 millimeters by 3 millimeters. And what I want to do is compare that to the first ARM processor that we produced in 1985. 3-micron technology, for those of you who remember at the time, 1 micron was the end of physics, couldn't build chips below 1 micron, wasn't going to happen, the world was going to come to an end. So I'd like to compare that 6K gate design. It wasn't really done in gates because we believed in pass transistors in those days, and flip-flops were bad, and it full custom design, and these things go in full circle. And if you look at our test chip, within that there's a little Cortex-M0 subsystem, and within that subsystem is a Cortex-M0 processor of about 8K gates. And sometimes I kind of explain to my kids, 25 years later, we've gone from a design team of 12 who produced 4 chips to make a complete chipset for a computer and had a compiler team, and did it in about a year and a half, through to about 100 man years of engineering to produce 8K transistors. And so it's interesting for me that it's worth our while as ARM investing in something as small and apparently simple as an 8K gate design, and how when you look at those two things, we've made enormous changes in what we've done to the ARM architecture, to implementation techniques, and it's been 25 years of real progress. You can see Moore's law drawn to scale. It's an absolutely tiny blob. What's interesting, of course, is economic chips have stayed about the same size, and if you go from that to a kind of 40G mainstream SoC that you'd find in a classic smartphone, it's about the same size, 7.4 by 6.9, but we've gone to 100 million gates. But we're still building the same kind of computers that we built 25 years ago, and we've managed to eat up all the transistors and write some software and still end up with broadly the same system. So that's 25 years of progress. R had to be for augmented reality. When you go back to the phone I talked about at the beginning, and I said we haven't talked about the apps. Within ARM, when we're looking at building system-level benchmarking and performance modeling for the future, the question is what software do you actually put on top of these systems that you postulate are going to exist in 2020? And what we've taken as the kind of driving function is augmented reality. And the reason I chose that is, what you get on the phone today kind of is a bit gimmicky, kind of works. What you see in people's research labs with, arrays of supercomputers are really cool. And you kind of think, well, one day that stuff that you see running on supercomputers is going to be what you're able to do on your phone. So if you can start to play with it as a toy today, maybe that's the driver. And I don't know if it will be the driver, but in terms of fixing some goals and driving a research program, we picked augmented reality. And some of this was stimulated when a friend of mine who knew some of the program said, there's this great app where you just take your phone and you point it at a sign, and in real time, it translates it. And it tries to get the fonts and the colours right. I was just so blown away with it, I thought, I'm going to buy that. It's a really great gimmick, and it was my first kind of cheap, really cheap iPhone app that I bought that I didn't need. And it's kind of word lens, and I kind of put it in the back of the drawer and thought that's fine. And then it turned out, I've got this Spanish translation app, what am I going to do with it? And that then turned into one of the most expensive holidays I've had in Mexico. Thoroughly enjoyed it. So, be careful with buying those cheap things, you don't know where they end up. S has to be for scale. I've talked about cubic millimeter systems in the past. I've talked about some of the cubic kilometer systems that have been built using ARM technology. Moving between those, I thought, well, how small can you get? So I kind of thought, well, if you took one of these cubic millimeter systems and just took the CPU out of the processor slice in that 3D module, which has sensors on the top, followed by a chip, followed by battery at the bottom. If you just took that Cortex core, what would it be in 2020? And how does that compare to red blood cells? And I had to cheat a bit, but if you take that processor, just take the processor, dice it up and make it into a 3D stack, it's about the volume of a red blood cell. So, we're approaching that world where those chocolate bar batteries start to operate. So, T has to be transistor. And for me, the good news is everyone tells me there's no proven solution for 8 nanometers and below. And I find that deeply reassuring. Because what it means is there are solutions up to 8 nanometers. And for me, that kind of maybe sees out quite a bit of my the rest of my active design life. So I'm reassured by that. And having lived through several generations of the end is nigh, we will never be able to go further, I'm quite confident that there will be solutions for 8 nanometer when we get there. I think they'll be costly. I think they'll have serious constraints on regularity on power. And the bad news is getting there. I think frequency's flat for constant leakage for the next 10 years. There are bumps and jumps as you go through different technology points that change it. Where you average it out, you're back to those trade-offs, and if you want frequency, you're going to have to pay for it with power. And there's no free lunch coming, it's just different trade-offs on how you get there. And if you look at how people build systems, there's lots of talk about, where does the power go in the system? How can I change my architectures to improve the power of my world? And, everyone says, well, of course, gosh, what a surprise. It's the system, stupid. You can make most of your power savings at a system level. But while that's true, what you can't lose sight of is that little bit at the bottom, implementation remains critical. So whatever great things you've done with your system architecture, you still need to find good ways of doing that implementation. And that continues to matter regardless of what other power-saving techniques you may have to employ to get there. U is for Uniprocessor. So I haven't used ARM data for this. I took this from paper. And it just shows that if you take a core and you push its performance, you see its energy go up that hockey stick. And so you then get to the point where you can go no further. And the last few percent are very, very expensive. And some companies are happy operating in that region, thinking it's the wrong place to be. But when you run out of performance, you have to go and increase your microarchitecture complexity. And if you plot that, you find we're getting to a world where those games are getting harder and harder. And this ties back to my scaling in servers. The microarchitecture complexities are starting to yield fewer and fewer gains. So, you're constrained at both ends, but the important thing to remember is you've got to design the right core. Because when you roll it all back and take the performance down, the power of each of those cores is significantly different. And so the smaller cores are more energy efficient than the complex cores. And that's what drove the kind of big little processing we're doing. You can't just take a big core, voltage scale it as low as you can go, and then run it slowly, because you'll be at the end on that top bar, and you'll be several factors of 2, 4, 8 power difference from delivering that low level of performance on a more efficient core. And so you can't design one core that scales from all of the performance you want through to the power you need. You have to have that switching, which is why we do the task and thread migration between big little to move the right process onto the right processor at the right time, because one unique processor isn't going to solve the problem for you. V8, hope you all worked out, I was going to finally get here towards the end. So today we've announced our first 64-bit architecture, and it's the beginning of quite a long road to 64-bit products. So we're not doing kind of product announcement, we're announcing the architecture. And the reason we're doing it today is that it takes time to build ecosystems, and we're fully aware of that. And we want to get the V8 architecture out there to allow developers to start developing software stacks that build on top of the hardware. So we're announcing it now to drive that adoption in the future. ARM V8, like all of its previous versions of the architecture, fully backwards compatible, supports the enormous legacy there is of 32-bit ARM VA software. We've spent a lot of effort in architecting it to ensure that it efficiently runs 32-bit code. It's not some monster new machine that's great at building 64-bit software. It's architected to do the 32-bit tasks really efficiently as well, so that we get all the benefits of where ARM is and scales to the future for those more complex and demanding applications that are coming. So a 64-bit OS can really efficiently support all of that existing software. Now, if you actually want to know more about the technical details, there is a talk at 2 p.m. this afternoon being given by Richard Griffithwaite, who is our chief architect. It's in Ballroom H. It's actually moved from what it says in the program. So it's in Ballroom H at 2 o'clock. And he will go through quite a lot of technical detail on that V8 architecture and how the 32 and 64-bit worlds interact with each other. And if you just kind of put that in a timeline, we've been working in ARM on kind of, the GNU toolchain, bringing up 64-bit Linux kernels. We got to today where we're releasing the specifications and models to our partners under under NDA, and then developing it out into the ecosystem so that next year we can actually build on developing that ecosystem with prototype systems coming out 2013 and beyond. So this isn't a quick thing, we're not going to go into this product tomorrow. It's building a new architecture and building a future. Because we see ARM scaling, we need to scale across the entire spectrum. W's for why things. This is my this was my birthday present to myself from my wife, and I just wanted to show how I think products have changed and how some of the kind of mobile world is changing products. So what are they? It's a pair of scales. I mean, they're quite nice, you know, I think they're very nicely designed pair of scales. But I didn't buy them, or didn't have them bought, because they were a nice pair of scales. It was actually guilt as a service. Okay? That's what I was actually buying into. So they are, of course, Wi-Fi enabled. You stand on the scales, and they go, you're quite light. You must be Mike's wife. That's quite heavy, you're Mike. It then uses the Wi-Fi link to push your data up into the cloud, and then on your phone you get this historical trace with trend lines and whatever else analysis you want of what your weight is. For me it transformed, because you go on the scales and you go, oh, it's a bit heavy. Yeah, but yesterday was special. I had to go out for a business dinner. I didn't really do that very often. And you only kind of remember the good days, and all the bad days just have excuses, and you get rid of them. But when it's actually mapped out there, the guilt is there, and, you know, that's the only thing that drives me is fear and guilt. So I think that's a good example of how products are being transformed, and everybody out there, you have to worry about what's the service component that goes with my product. Because the value, I think, is going towards those service-driven things rather than just those tangible objects, which in themselves have to be beautiful, but there has to be more beyond that. So X is for EXA, a bit of a stretch there, but forgive me, which is the whole exascale high-level, high-performance computing, and how do we get exaflop computing performance in the future. You know, IBM recently was the winner of those competitions with Roadrunner. We're involved in a European project called Blanc, along with the Barcelona supercomputer group. And what fascinates me about working with them is they have a different view of computing, because they're always concerned about, we've got a fixed megawatt budget, how are we going to use it? So they think in megawatts, whereas I'm thinking kind of microamps. And joining those two together has been really interesting. And it's a scale-out problem, okay? They're going after problems that have massive scalability. And so it's interesting to see how we can build kind of 50 petaflop racks as the first prototype that can then scale out. It's not world-beating at that point, but it's our first kind of serious step towards driving those megawatt solutions that kind of matches my cubic millimeter to a cubic kilometer scale. Why has to be for you. I'd like to thank you all for having come to TechCon. I hope you're getting a lot out of it, and I hope you take away some of the messages from this. Conclusions. Now, I was going to talk about zebrafish, because I really like zebrafish and the way that they can regenerate themselves and grow. But I was told, no, Mike, that you actually have to have some conclusions. So, very simple message. You know, if you're in the world of energy-constrained systems, and for me, everything is now an energy-constrained system, whether it's 7 megawatts or whether it's a few milliwatts, it's an energy-constrained system. The solutions to those are all about building heterogeneous solutions. It's not monolithic, it's not homogeneous, it's a heterogeneous world. And the Internet of Things is a driver that enables and interconnects all the things we're going to see in the future. And it's the service, stupid. Okay, thank you. I'd now like to welcome Ole to the stage. He works for the UN. He's the head of the UN Corporate Sustainability Program called LEAD. Arm's very proud to be a member of that organisation, and we've set ourselves targets for what's our CO2 reduction for employees of Arm. But that's not important. I think what's important is how does Arm technology actually enable everyone to build systems that can transform what global sustainability is about. It's not about us, it's about what Arm products can do. Thank you.
Great.